Launch a rocket straight up, and it eventually crosses the boundary of space. But without sideways momentum, gravity immediately pulls it back down. To stay in space, a vehicle has to achieve orbital velocity. That requires traveling parallel to the ground at roughly 7.8 kilometers per second. Isaac Newton pictured this as a cannonball fired from a high mountain. If the ball moves fast enough horizontally, the curve of its fall matches the curvature of the Earth. The ground curves away at the exact same rate the object drops. Reaching orbit requires outrunning the planet's surface, rather than just escaping its atmosphere. This animated ledger tracks the delta V budget, the total change in velocity a rocket has to generate to achieve that 7.8 kilometers per second. Hovering vertically costs energy. Every second a rocket spends fighting its own weight during an upright climb, gravity extracts a toll, demanding an additional 1.3 to 1.8 kilometers per second of effort. Pushing through the thick lower atmosphere and steering the vehicle against aerodynamic forces exacts another penalty. Together, drag and steering add roughly 0.3 kilometers per second to the final bill. Launching eastward from the equator provides a strict mathematical discount. The Earth's rotation gives the rocket a free 465 meters per second of starting momentum, leaving the true cost to reach orbit at about 9.4 kilometers per second. That total delta V requirement dictates the exact mass and shape of every machine reaching orbit. In 1903, the Russian scientist Konstantin Tsiolkovsky calculated exactly how difficult paying that velocity bill would be. This chart plots required delta V on the x-axis against mass ratio on the y-axis. The curve is logarithmic, meaning higher speeds require exponentially more fuel. To reach 9.4 kilometers per second, a rocket must achieve a mass ratio of 15.4. Translated into physical reality, 93.5% of the vehicle's total liftoff weight has to be pure liquid propellant. A launch vehicle is a fragile metal tank constructed almost entirely to lift its own fuel, leaving barely any capacity for actual cargo. Newton's third law of motion provides the physical mechanism to generate that speed. The rocket pushes mass in one direction to accelerate in the other. Chemical reactions inside the engine ignite the propellant, accelerating a small mass of exhaust gas to hypersonic speeds. This pushes the massive vehicle upward. But a single vehicle carrying all that fuel eventually empties its massive lower tanks. That empty metal structure becomes dead weight, accounted for in the structural coefficient. The only physical solution to Tsiolkovsky's equation is staging. As the rocket climbs, it jettisons the empty lower fuel tanks. The remaining engines then push a drastically lighter vehicle. Discarding the empty structure breaks the mass constraint, allowing the remaining thrust to push the vehicle all the way to orbital velocity. At liftoff, the rocket flies completely vertical to climb out of the dense lower atmosphere, fighting a direct battle against gravity drag, where every second costs 9.8 meters per second of delta V. Because orbital velocity requires horizontal movement, the vehicle must eventually tilt its nose downrange to build speed as early as the atmosphere allows. Gimbaled engines actively pivot, redirecting the angle of their thrust to mechanically steer the rocket toward the horizon. This vector graphic illustrates the gravity turn. The vehicle's turning rate exactly balances gravity, maintaining a near-zero angle of attack. This precise trajectory minimizes aerodynamic stress on the hull and conserves precious fuel by letting Earth's gravity do the work of bending the flight path. The gravity turn relies on the planet's own pull to transform a vertical escape maneuver into horizontal flight. High above the atmosphere, the final upper stage burn completes the 9.4 kilometer per second requirement, balancing the mathematical ledger. The vehicle enters a parking orbit in low Earth orbit, a stable, circular state of permanent freefall around the planet. From this altitude, the rest of the solar system becomes accessible, using specific maneuvers like Hohmann transfers and the Oberth effect. Burning fuel deep within Earth's gravity well multiplies the efficiency of the engines, generating the momentum required to reach the Moon and other planets. The overwhelming majority of the energy required for spaceflight is spent achieving those first few hundred miles of altitude and sideways speed. Once that initial bill is paid, the vehicle stops fighting Earth and begins navigating the cosmos.